The number of these possible vacuum multiplications is greater than 10 to the 120, then this would be enough to explain the fact that the vacuum energy is so small. It was written in '84. It was before Steven Weinberg's constraint on value of cosmological constant and his anthropic prediction of the situation. It was before me, and it was equally ignored later until the recent discovery of the cosmological constant, after which suddenly this idea became very popular among some and very unpopular among some, but this is just a lesson of history.
Alex, and please speak up, we can't hear you usually. So.
I'm used to yelling in classrooms of 800, so I wanted to just go back to the multiverse thing. You know, if we end up finding that the evidence for something like inflation continues to grow and grow and grow, and I would say that the evidence for it or something like it is now pretty good, and if inflation naturally leads to something like a multiverse, then I'm quite comfortable thinking about the multiverse, and I think that's the stage we're at right now. That, correct me if I'm wrong, Andre and others, but it's very difficult to have inflation models where it only happens once. It should happen all the time, over and over again. They butt off from one another, right?
No, this is not correct.
Well, I've read your papers.
No, be careful, be careful. You read my papers or the papers of people who...
Well, I read, even in your Scientific American article, you have all these quantum fluctuations.
You asked me a question,
yes.
I'm answering.
Okay.
So suppose you have a theory m squared phi squared.
Yeah.
You have eternal inflation there. Suppose you have theory which is m squared phi squared just during low scale inflation like 60 foldings, and after that it becomes exponentially steep. No eternal inflation there, period.
But I thought quantum fluctuations lead to new regions.
No, this is just a wall. This wall stops you at the time when you want to come to the region where eternal inflation starts. I know that some people in extreme excitement of just like the idea, they say that eternal inflation is inevitable. It's inevitable if you have some structure where you have metastable vacuum state, de Sitter state, where when you fall down you can rise up and jump one over again. This is not the simplest model of inflation. This is, however, what your discovery suggests.
So, Alex, I would also add the advice of Carl Sagan. Extraordinary claims require extraordinary evidence. And I would think before we want to buy the multiverse, we would actually want to see stronger evidence than equations predicting it. Even if we thought the equations really predicted it and we had a firm theory of inflation.
Michael, I have one comment, but before that, maybe we were supposed to have a discussion after this.
Isn't that what this is?
This is it. So why don't we just have this as a discussion?
That's why I kind of think you're
So let me come to my point. It's hard to disability model. In fact, I only was in math and disability, and it's very reasonable presentation you gave. But there's one point in which I find myself in strong disagreement. And it's not just myself, there's a number of people in the scientific community about this. What Francesca was saying, you had this, it seems to me that of the three problems on which you focus, the dark matter, which the short stories with good ideas, we're totally confused. Inflation, which goes with it, which we don't know what's the metaphysics behind it, whether it's invisible. The third problem, lambda, is a completely different story, in my opinion, and in the opinion of many. It's a really different story because, of course, it might be that W is not minus 1. Of course, it might be that there is some strange physical behind it. But to say that this is the biggest mystery in science, like this, today's science or cosmology, it seems to me is based on confusion. The confusion is between the fact that in quantum field theory, constants get negative correction These are infinite. And the fact that there is lambda. At some point, lambda was measured, and a large part of the community said, oh yes, we know what it is. It is vacuum energy. Oh, strange. Vacuum energy is infinite. So how can it be infinite? Now, if the point I want to make is that if I take the charge of the electron and I compute it in quantum field theory, it's infinite. More close to it, because the correction of logarithmic, but more close to it, if you take the mass of the Higgs, which is not logarithmic, it's polynomial. If I compute it in quantum field theory, it is infinite. So the fact that I get infinity, or that I get 10 to the 120, is just picking up the Planck scales that I often and use it, is not specific of lambda. It's all the constants in fundamental physics. The people who...
But isn't that why people believe that quantum field theory is not the final answer?
Absolutely.
That your theory should not answer you with infinity.
Absolutely. So the problem is, quantum field theory is something we have to understand in quantum field theory, and we have to understand it better. That's fine. But this is not the specific problem of lambda. Then lambda has other peculiarities. If
cosmology put it right on the front table and said, no more putting it in the background and ignoring it, because something like lambda is causing the universe to speed up, and so this problem better come to the front of the queue.
Right, but we have a fundamental general relativity from the point of view of the relativists. In the infrared, let's not care about it as well, it has to be described by two constants. So on the point of view of quantum field theory, these two constants get radiative correction to infinity, so you have to measure, and what you measure is the difference between the layer and according to the standard quantum field theory way of thinking. This is the way people do a rigorous quantum field theory because space-time think. This is the way many relativists think. So I'm not saying perhaps the dark age is something different. What I'm saying is that here we have a perfectly good theory, as good as the rest, and as bad as the rest. And I don't see more mystery than the mystery of the mass of the charge.
Or I can say it another way, that because of history, we discovered the gravitational constant first. We discovered lambda second.
Exactly.
And so we ascribed the gravitational constant problem to the hierarchy problem, and ascribed the lambda to vacuum energy. But what if we lived in the universe where we discovered lambda first?
Exactly.
And so gravitational constant second?
One
We'd be
thing-
having a similar discussion like this.
Yes.
One thing that we know in science
Sure.
is we never ask the right question the first time. That the most important thing is asking a question. And the other important thing I would say, get to quote another U.S. president, the soft bigotry of low expectations. So we should always set our expectations really, really high, even if we can't meet them. So I'll just mention Murray Gell-Mann, of course, touted string theory as being the unique theory, the only way to unify gravity and quantum field theory, and we now know that's it's not a unique theory. And it may work out in the end that our high expectations don't work out, but I'll give you one example of where they did work out with the helium. So Fred Hoyle was the first one to point out that the universe had a primordial abundance of helium of 25%. And so we could have just said, well, whatever, that's just the way the universe was born. It had to have some composition. And one of the great triumphs of this, what Weinberg called as the standard model, is it's automatic.
I'm not saying that it's wrong to study different ways of doing that. I'm saying that we should keep in mind that it's good impression, but we might have the wrong questions. And that
Absolutely,
science
I agree.
is full of wrong questions. Kepler struggles for years on the wrong question, namely, to understand the dynamics of the solar system, we have to understand the ratio of the distances of the planets from when he dropped that question, he said, no, forget about that. Let's do something else.
That's the history of science. We always ask the wrong question first. The important thing is to ask a question.
So the great
and then-
mystery about lambda might be the wrong question.
But it's not a new voice about here.
Yeah. As a particle physicist, I have to comment on the lambda as being, because once we put it on the right-hand side as part of helium, we have to, in a sense, say something why this value is such and not different. And with the lambda,
So don't
particle
put
physics,
it on the left hand side.
on the left-hand side is in a gravitational plot.
Yeah.
So we can say, okay, it's a constant, but once we put it to the right-hand side, so in a sense it's part of cumulative, part of kinematic or dynamical picture, we have to explain this. Because once we have, for example, the great problem of particle physics is mass of the Higgs. Yes, that's a hierarchy problem. And it's square of the problem of the cosmological constant. And still there are many, let's say, ways to supersymmetry was invented, partly to kill the corrections to the mass of the Higgs. There are other solutions. But with the cosmological constant, when we try to treat it as a part of the vacuum expectation, whatever, we have an enormous problem that once you fix it, and you make a slightest deformation, or you add a new field, or you change your parameters, this gets enhanced, incredibly enhanced. The lambda changes dramatically once you do anything with your parameters, with whatever. With the charge of the electron, with the mass of the electron, you change it, you have logarithmic change. Nothing really changes. But with the cosmological constant, once you start to play a little bit with any of your mass of the electron, charge, whatever, it's enhanced enormously. So that's why the problem of the cosmological constant is a huge one. That's not the problem that once you put mass of the electron or electric charge, something, and you say, oh, I will change it, I measured something better. You change only very, very little mass of the electron. You don't have to care for it. But once you calculate the cosmological constant, any slightest change in your parameters is enormously enhanced. And you have to explain that this lambda comes from nuclear energy, mass of the electron, what are completely different areas of physics, and still they contribute. So you have to, in a sense, measure them, all of them, or cancel them with incredible precision, even coming from a completely different areas. That's the problem.
Can I?
Yeah.
So I showed this picture, and the fact is that if you have plenty of vacuum, and only some of them initially are of a small value, and many others are all over the place. And then you look at the quantum theory of the kind was explained, and maybe this new little area, which is where we want to be, some vacuum came from very high values. So it is not that we are able to preserve the very tiny cosmological constant at the classical level after quantum corrections. And this is the only way to address 10 to the minus 120. Because they could come after whatever. You still have plenty of them today. And this is the only way to address this in extremely small value. Because if you say, I will correct it, then there is no way to preserve it. So you have to start with huge amount of vacuum everywhere, and then allow the possibility that there is, after all possible quantum influences, you still have many which are 10 to the 120 over this area.
So if what Renata says is correct, I think that would be evidence that the lambda problem is the most profound problem of
Yes.
science.
Thank
And
you.
I'll just add a quick, some of you know that I coined the term dark energy, but probably most of you don't know why. And the reason I did it was the astronomers said, that's just lambda, and we're just going to go measure it. And you can see how well you can measure it if you assume that it's lambda and not something more profound. And so the idea of dark energy is to say, not so quick. It could be much more, I think it's much more, and that's my opinion, I think it's much more profound. But my opinion's worth that. My opinion plus $2.25 in the United States will get you a cup of Starbucks. So next time you go to Starbucks.
So I just want to put a very small remark. So we should distinguish two concepts. One is the concept of the multiverse. So the string theory, we know in the domains that we can control and understand very well, the string theory has essentially infinite number of vacua, but all of those that we can control are in Minkowski or anti-de Sitter. So the question is, no, sorry, then we can debate, but let me just finish the remark and then we can debate. Now, Now, the one, so the question is not about multiverse. Multiverse, I think it's a fact. I mean, nobody disputes that string theory has infinite number of solutions. Already QCD has infinite number of vacua, theta vacua, right? So it's not surprising that string theory has many vacua. The question is whether there is even a single string theoretic vacuum in the sitter. And no, I understand your opinion. But what I'm saying is that this is something. So you see, we have a theory, and this is an answer to a question. We just so this is either yes or no. I mean, we can. So the problem that we disagree on that, but the problem is that all these vacua that have been demonstrated in the sitter, they are not really trustable. There is always an assumption. You dig it far. We can dispute it anytime. Okay.
There's a large community.
We disagree. I understand. There's a number of community in science sometimes that decide because there is a theory and there is truth, right? Either there exists the sitter vacuum in string theory. I mean, there is nothing to laugh. This is an answer to a question. We can dispute. We can discuss. And I mean, I can. You give me any example that you think it demonstrates that there is a trustable vacuum, and we discuss.
So shall we discuss it later?
Sure. Yeah. You started the discussion. I was not gonna. But my point was not to debate. If you are right, I'll be very happy. Fantastic. Okay. It was very good. Because right. You see the different things. What I'm saying is that this is an answerable question. And my personal opinion would be that it would be fantastic if the prediction of the string theory that the cannot be the sitter is true, because this would be a prediction from a quantum theory of gravity that was modular constant is zero. Then why it is small, maybe you can explain in some other way.
I want to be a little bit on what I already said, because I think lambda is definitely not a problem of particle physics or quantum theory, because without Newton's constant, there would not be a problem with lambda. There wouldn't exist a lambda, or it would be a background of that of some sort. But it would not belong to particle physics. It would just describe space-time. So I think lambda the lambda problem comes about when we try to quantize gravity. Now we know there is a much bigger problem in trying to quantize gravity. That constant traps have a state value. So I think we try to, quantum field theory without gravity also has its problems, because then infinities all become real, because they explode way beyond the Planck scale in a way that you don't want. So quantum field theory needs gravity, that is true. But to quantize gravity, you need much more than quantum field theory. So if you look at the problem of quantizing gravity and quantum field theory, and you then add nothing at all, then you have a lambda problem. But we all know there must be much more. So even personally, I have my doubts of quantum mechanics itself. It would be a big step into no one's hands today, because nobody understands how to do any physics without quantum mechanics. But that would be a big change, and I think only if you understand how to do such things, you'll finally get some theoretical understanding of matter. I think before that, it won't happen. So, and particle physics will thrive quite well without any knowledge of matter.
I guess also that what happens when we are discussing vacuum energy and different vacuum, there is certain abuse of language. And the abuse of language is obvious to everybody who will know that in the model, the standard model of elementary particle physics, which is sort of helped to develop, many people got Nobel Prizes, including their group, but also Lemaitre and others, and the theory and the discovery of the Higgs field, Higgs particle actually, shows that we live not in the empty space, but in an empty space with the classical scale field of the magnitude, which is calculable. So there is an absolute mystery. How is that the whole universe is filled with this scale field, and it has no energy? So it's not the question about quantum gravity corrections or anything. It's just a question of why scale field after spontaneous, and that's important, after spontaneous symmetry breaking, because the height of the mountain from which this field falls down in the electric theory has energy density many orders of magnitude larger than nuclear energy density. So this is one of these things, and then if the theory is grand unified theory, then you actually were falling from the much higher hill And therefore, the fact that we are ending up nearly zero, it has, well, it has, of course, relation to quantum gravity. But the quantum gravity is not the only source. It's just the possibility of other sources contribute, and we know that at least some of them do exist.
Andrei, that is solved precisely by string theory, which predicts that constant is zero.
Oh yeah, we have
That's the solution. No, I'm serious. That's the solution.
There's also the solution that vacuum energy does not gravitate, and this is what happens in unimodular gravity.
Yeah.
So
That's also
I don't see George Ellis around here, but he's been.
Yeah, no, that's also possible.
That is right, a possible solution,
Yeah.
right? And it's very simple.
Of course, the only question would be why we have right now 10 to the minus 103.
Then it's just some number that.
Yes,
But,
this is agree that this is a very unnatural number, and the fact that we see it only right now after exactly this 14 billion light year, 14 billion years, it's a mystery because there is nothing special about it except for that we are living and making observation at the time when the energy density of all the rest matter becomes equal, or almost equal, slightly less than the vacuum energy. So it's a mystery, this 10 to the minus 103. Otherwise, you just assume that this number exists.
Of course.
So Gerard, I have a quick question for you. So if there were no gravity, and you just had quantum field theory, wouldn't it bother you that some of your calculations were infinite?
Yes.
Yeah.
No,
Yeah,
that I agree. So, quantum field theory without gravity will also have tremendous problems. And we believe that quantum gravity will somehow solve endeavors, say, the infinity problems. So we can't do without gravity. But I think that to combat gravity, you need much more than just regularize or something like that. So I think that to understand gravity, you need so much more that the problem with lambda should be postponed until we understand better how to handle gravity. But of course, you can say right now that the problem is waiting for us. It will be an important problem no matter what. So that much I agree that we want to understand where it comes from. So we put on the shelf is important unsolved problems. But other problems are much more important. I think we want to understand how physics works at quite scale. And that's a much more complicated, complex of questions that we want to answer. Whereas the cosmological constant is just one number that we're puzzled about. It is a number, we are puzzled about it, it's waiting there to be solved, but there are, to my mind, much more urgent problems.
Although the United States funding for astronomy depends upon being able to tell Congress when the lights out time is. And until we know about what dark energy is going to do, we can't tell them with any. This is supposed to be a joke. The destiny of the universe depends upon knowing what dark energy is. And we have an argument right now that the universe is accelerating, and so we won't be able to see most of the universe soon, and so it's the time to fund astronomy.
And they do not give us money now, then because of the eternal inflation of the universe, their money just vanishes. So pay us now, otherwise it will be too late.
We're sort of beginning to run out of energy. Does anyone else have some comment that they want to throw in right now before we terminate the discussion?
About what?
Anything. we've had a huge range of subjects today, from trying to understand black holes and Sharper was talking about. Now was talking about observational problems of studying supermassive black holes, trying to understand cosmology, dwarf galaxies. It's a huge range. Yes.
One question to get on how you promised me an answer yesterday, but I didn't hear it. So let me rephrase the question. I take your model of black hole seriously, and I find a contradiction with what I studied in my general relativity class, which is the following: that if there is a very large black hole, many billion solar masses, and I happen to navigate near the horizon, I studied that I can happily cross the horizon. Around me I see a sort of Minkowski with a little bit of curvature. I can bring me an encyclopedia with information, I move it inside, the information is inside, And therefore, that information is either lost outside or doubled. Both things being somehow in contradiction either with the model or
Yeah,
with the
okay.
model. Where is the
It's
confusion?
hard to say all these things right in a short amount of time. But imagine the following. Look at the time axis. Strictly speaking, when you pass through the horizon, you are at time equals plus infinity for the outside observer. So when you go after that, it's infinity plus another number.
Yeah.
That is the amount of time that you spend behind the horizon. Now, so the dumping only happens that before time went to infinity, all the information of encyclopedia was sitting outside our universe. It had already come in form of water flight, it was come outside, so it's there. So it never got lost, it was outside already. But after time's infinity is over, that encyclopedia is lost again. Now it's inside, we're in the hands of the guy who just went into the black hole. So the whole thing is, if you look at one time axis, you say, okay, there was a time before the observer went into the black hole, there's a time after he was seen to go into the black hole until infinity, and then there's time after that. Now, this encyclopedia and all these three structures was somewhere else. So before the observer went to the black hole, he was carrying the encyclopedia in his hands, ready for it to read, then he went into the black hole, but the information encyclopedia went out, but heavily mixed by Fourier transformation, so unrecognizable, but it came out. And then the universe came to an end, and then the information back in the encyclopedia again for this observer who was carrying it along with him. So the information was always there, always a wave function where you have that information. But you have to, so if you time separate the events, then there's no contradiction between the quantum numbering anymore.
So you're not saying that there's anything wrong with what they said about cross the horizon? Not at all.
No, you can have it two ways, so to speak. You can have this guy who went into the black hole because he is not interfering with the rest of the universe because time's infinity was over, and so only then he was open his encyclopedia and read it inside the black hole.
Maybe you can answer my answer?
Sure.
I mean, I certainly don't think the information is repeated because that would be real problems with quantum mechanics and so on. The information isn't lost when you're inside because it's there still when you're with the encyclopedia. However, people outside aren't going to be able to read it, that's irrelevant. However, when you get crunched up on the singularity, yes, it gets lost, it gets chewed up by the singularity, and that's the end of it. And I don't see any trouble with that, except that it's inconsistent with unitarity, but that's all right.
That information is lost,
Yeah.
while Hera assumed that somehow inscribed why this information is
I'm
not
not
lost.
assuming it on computers. I mean, it's just a question of
Okay,
calculation.
sorry, is stating that information is not. So there is a difference.
I'm
Physics in there.
I just give you my view.
Yeah.
Well, I think this agrees because singularity is there in classical limit when h bar is 0 and L Planck is 0. And in classical limit, black hole is eternal. So it's perfectly fine to have this statistical value to go there forever. And that's fine.
Well, but the question is, the information encyclopedia is on scribe class or not?
No, I'm saying classically there is absolutely no problem that you put a box and you never open it. Take your encyclopedia, put it in a box, you never open the box. There is no paradox or there's no unitarity violation. Unitarity violation would be if your box evaporates and then you see nothing, right? But this singularity that was referring to is the singularity in the classical theory. In classical theory, black hole is eternal. When h bar is 0, there is no evaporation, so it's an eternal black hole.
We're not talking about classical theory, we're talking about the whole thing, the real thing.
Yeah, but in real thing,
There's no
you understand, but in real thing, how do you know that there is a singularity?
Well,
But-
actually, it's not in my theory at all. That's
Right, then-
I don't care about it because it's beyond time.
I understand, but
So nobody who watches these black holes can ever notice any effect of the singularity.
Sure,
It's
that's
too far away.
absolutely. But that's about what I'm saying is that the moment you resolve singularity, that you can have a model in which you resolve singularity, quantum theory of a black hole. What I'm saying is that that model will, by definition, will never be in contradiction with the classical singular black hole, because classical singular black hole is eternal.
But there's
Yeah,
no
that's all.
need for such a thing.
Huh?
I think there's no need for that.
No, I agree, but I'm saying in the classical limit everything is fine. There is no information problem in classical or semi-classical limit.
That is true.
Because black hole is eternal.
Okay, but
Alex,
now discussing the quantum case, and now
Yeah, sure, I agree.
now the question is where the information go. I say, well, it looks like, it seems as if it's doubling, which is absolutely
No, it's not.
So
No,
it seems as
you
if
cannot.
But it's not.
I agree.
Because,
Yeah,
because the moment that this observer opens his encyclopedia when he's inside that hole, the whole universe has already come to an end. So for the outside observer. So there's no confirmation.
So I think
It's
we
not
should
doubling.
think about stopping the conversation because we have to go and freshen up before dinner, but I would like to have, Alex, why don't you have a final word right now?
Well, I just, as an ignorant observer, I don't understand why in the classical theory there's a problem, since because of the infinite time dilation, the material never gets
That's
into the
another
black hole
way.
anyway.
Absolutely, that's another way to see it.
Okay.
Yeah, in your reference frame.
It's only when you bring in quantum mechanics and you let the thing evaporate
Absolutely, yeah.
that, there's this big debate about whether information is lost or not.
That's absolutely
Right. Okay, good. I'm glad my understanding is okay.
I would like to make one very last comment that this, which is an observation. It is clear by listening to all of you that today we won't be able to solve the cosmological constant problem. So I suggest we stop and we gradually go to.
Can I add two things?
Yes.
One is, we would really like you to sign the book here because there
Oh,
certainly
yes.
are very famous
Thank
people
you very
here.
much for that. Sign the book, please. Yes.
And the other thing is I'd like you to all give us a round of applause.